Right now, on the southern flank of the Big Island, a slab of rock the size of a small country is creeping toward the Pacific Ocean at about 10 centimeters a year. You can't feel it, you can't see it from a helicopter. But GPS sensors bolted straight into the volcano have been watching it for decades, and they don't lie. The whole south side of Kilauea is unbuckling from the mountain. Geologists have a name for what happens when a piece of a volcano this big lets go all at once. They call it a flank collapse, and if it happens the way it's happened before, the wave it throws could easily sit higher than a 40-story building. I want to clear up the stakes here before we get into any of the science. We aren't talking about the typical tsunamis you see on the news. I don't mean the ones that roll in over a few minutes at 15 or 20 feet and wreck a shoreline. Those are horrifying enough on their own. But this is something else entirely. When a massive chunk of a volcano slides into the ocean, it doesn't push the water out of the way gently. It slams into it. A landslide of rock and ash with the total volume of a mountain range hits the ocean at highway speed. That water has to go somewhere, so it goes straight up and then it surges out across the entire Pacific. What keeps some scientists up at night is that this isn't just a theory somebody pulled out of thin air. You can actually see the marks left on the seafloor around Hawaii. Plus, it's written into the cliffs of a neighboring island in a way that makes no sense unless something massive happened there. Let's look at the evidence that turned this from a crazy idea into a real scientific debate. Back in 1975, the U.S. Geological Survey started dragging sonar equipment across the ocean floor around the Hawaiian Islands. They were trying to make a basic map. Instead, they found a massive graveyard, spread out across the seabed, sometimes stretching over 100 miles from shore, were huge fields of scrambled debris. We're talking blocks of rock the size of Manhattan. One single piece mapped later was about 30 kilometers across. That's not a boulder. That is a piece of an island that snapped off and slid for miles across the ocean floor before coming to a stop. Researchers counted at least 17 of these giant slides around Hawaii. Some of them rank among the largest landslides known anywhere on the planet, land or sea. They're bigger than anything the continents have ever produced. All of them broke off the sides of these volcanoes as the islands grew too heavy and shed their own weight straight into the ocean. That map brings us right to the island of Lanai. If you sail to the southern coast of Lanai and look up at the hills, you'll spot something that stopped a young geologist named James Moore in his tracks. High up on the slopes, hundreds of feet above where the ocean sits right now, there are deposits of marine coral, broken shells, and beach gravel. That's ocean debris sitting on a hillside, way above any normal tide. In some spots, it sits over 300 feet up. How does seashell gravel get 300 feet up a mountain? Moore and his colleague George Moore published their answer in the late 1980s, and it caused a massive stir in the geology world. They concluded a giant wave carried it there, specifically a wave that ran up the slopes of Lanai to a height of more than 300 feet. They pointed to these deposits as proof of a mega-tsunami, linking it to a flank collapse off nearby Molokai, where a huge piece of the volcano slid away and slammed into the ocean. The splash ran up Lanai's shoreline like water sloshing out of a kicked bathtub. 300 feet is a wild number to wrap your head around. The biggest wave to hit a modern Hawaiian resort might be 20 or 30 feet in a severe storm. This was 10 times that, easily. And Lanai wasn't even the spot where the landslide happened. It was just the island sitting next door. Now, not everyone agreed with this, and I want to be honest about that. The science here is actively debated, which actually makes it way more interesting. Some researchers looked at those same coral deposits and argued they were lifted by the slow tilting of the islands over hundreds of thousands of years, rather than tossed up there in a single afternoon by a massive wall of water. The debate got intense, and people built whole careers around defending their side. But nobody could ignore the debris fields sitting on the ocean floor. Those blocks are real. Those slides definitely happened. The actual debate is just about how fast and catastrophic the movement was, and how big the resulting waves turned out to be. Which brings us right back to the volcano moving today, Kilauea. Kilauea is the youngest volcano on the Big Island, and its entire southern flank, an area called the Hilina Slump, is the exact piece geologists monitor most closely. It isn't small either. The moving section covers about 5,000 square kilometers, mostly underwater, stretching down the submarine slope for miles. On land, you can see its edge at the Hilina Slump, a series of steep cliffs that step down toward the coast like giant stairs. Those cliffs are fault lines, showing where the slump is pulling away from the rest of the island. Most of the time, the slump just creeps along. It's slow and steady, moving about 10 centimeters a year, which USGS and University of Hawaii GPS stations measure down to the millimeter. 10 centimeters is roughly how fast your fingernails grow, so it isn't something that causes panic on a random Tuesday. The problem is that the Hilina Slump doesn't always stick to a slow creep. Sometimes it lurches. On November 29, 1975, the ground beneath the south coast of Kilauea gave way in seconds. A magnitude 7.2 earthquake dropped a section of the coastline by more than 3 meters and shoved it toward the ocean by up to 8 meters in one sudden move. The quake killed 2 campers at Halape on the coast. It triggered a local tsunami that surged up to 45 feet at Coho. Campers were washed off the rocks in total darkness, and survivors had to grab onto whatever they could find as the water pulled back and rushed in again. 45 feet of water, all from a slump that only moved a few meters. Imagine what happens if the slump doesn't stop after a few meters. What if it slides several kilometers instead, just like those ancient collapses that left massive rock blocks scattered across the seabed? That's the difference between a local disaster and a catastrophe for the whole Pacific. It's the exact same mechanism, just on a vastly different scale. Then came 2018, which made all these abstract concepts feel very real. That spring, Kilauea's summit began collapsing. Magma drained out of the volcano's internal plumbing and burst through fissures down in Leilani Estates, burying over 700 homes in lava. But the lava wasn't the only major event. On May 4th, 2018, a magnitude 6.9 earthquake struck that exact same southern flank. It was the strongest quake the island had seen since 1975. The whole south flank jumped seaward again, with GPS stations catching the coast lurching half a meter in an instant. Half a meter, all at once, right on the fault line geologists consider the most dangerous slope on the island. It showed everyone that this slump isn't some ancient history detail. It's active, it shifts, and every single time it moves, it heads toward the sea. So the obvious question is whether Kilauea is actually set to collapse and send a massive wave across the Pacific, or if this is just fear-mongering dressed up as science. To give you the honest picture, the catastrophic version with a sudden, full-scale failure is physically possible. The geologic record shows it has happened around Hawaii before. However, it seems to be extremely rare. Those huge debris fields on the ocean floor built up over hundreds of thousands, maybe millions of years. The massive slides that created them are spaced out over huge stretches of time. On any human time frame, the odds of a total collapse happening are very low. They're low enough that no geologist is advising anyone to sell off coastal property over it. At the same time, nobody knows the actual trigger point. No one can say how much strain the Hilina Slump can handle before a slow creep turns into a sudden collapse. It moves by inches for decades, then jumps meters during an earthquake. What scientists can't completely rule out is a jump that keeps going. A cascading failure where the moving block loses its grip, speeds up down the slope, and drags a piece of the volcano into deep water with it. That's the main worry, and the gap between a routine creep and a major failure comes down to questions about scale that we can't fully answer yet. That uncertainty is why it's worth paying attention to without getting overly dramatic. The physics behind a Hawaiian flank collapse explain why it would be so much worse than a typical tsunami. Once you look at how the water moves, that 300-foot deposit on Lanai stops sounding like an exaggeration. A standard tsunami, like the ones in Indonesia in 2004 or Japan in 2011, happens when the seafloor shifts. A portion of the ocean crust snaps up or drops down along a fault line, pushing the whole column of water above it. It's an efficient way to send energy across an ocean, but out in deep water, the wave itself might only be a few feet tall. It only stacks up high when it hits shallow coastal areas. A landslide tsunami works differently. When a mountain-sized block of rock drops into the ocean, all that kinetic energy hits the water in one specific spot. fast and shallow. Near the source, the wave can be insanely high because the water displacement is concentrated. We've seen smaller versions of this process that prove how it works. In 1958, in Lituya Bay, Alaska, an earthquake knocked about 30 million cubic meters of rock off a cliff directly into a narrow bay. The splash on the other side surged up the opposite slope, stripping trees off the mountain up to a height of 1,700 feet. That's over 500 meters of wave run up, making it the tallest tsunami ever recorded. And it came from a landslide that was just a fraction of the size of a Hawaiian flank collapse. 2 fishermen and a boat actually survived it. They described the water rising like a whale's back beneath them, carrying their boat right over the trees on a spit of land. Scale that up. Lituya Bay was 30 million cubic meters of rock. A Hawaiian flank collapse involves hundreds of cubic kilometers. That isn't just a bit bigger, it's thousands of times larger. Looking at it that way, coral gravel sitting 300 feet up a hillside on a neighboring island starts looking like the exact result you'd expect if a chunk of Molokai the size of a city crashed into the sea. The reach of the wave is what makes it especially serious. A landslide tsunami loses its energy faster than a fault-based tsunami as it crosses open ocean, which limits some of the impact. Still, computer models show a major Hawaiian collapse would send dangerous waves across the Pacific to California, Mexico, Japan, and South America. They wouldn't be 300 feet high when they arrived, but they could still be tens of feet tall hours later, arriving out of nowhere with no local earthquake to warn coastal areas first. So, who monitors this? And how would we get a warning if something started? The USG's Hawaiian Volcano Observatory keeps one of the densest monitoring networks in the world focused right on Kilauea. GPS units track every millimeter of movement on the flank. Seismometers pick up ground tremors, from tiny fractures to major quakes. Tiltmeters track the surface inflating or deflating as magma shifts underneath. Out in deep water, DART tsunami detection buoys sit ready to register sudden wave movements and send warnings to Pacific coastlines. The main reason for all this gear is timing. A slow creep needs no warning because nothing sudden is happening, but a major collapse would likely give clues first. Scientists expect we'd see a rising swarm of quakes and accelerating shifts on the GPS logs, with the flank moving faster in the days or hours leading up to a slip. That's the hope, anyway, though a sudden failure without much warning can't be ruled out completely. Nature doesn't always give a heads up. There's another factor here that changes how you look at the whole system. Gravity isn't the only force pulling on the flank. Every time Kilauea fills with magma before an eruption, it expands and shoves the south flank outward from the inside. The volcanic eruptions and the landslipping are directly connected. The exact same magma movement that creates famous lava displays is also pushing the mountainside toward the ocean bit by bit. The scenery and the hazard come from the very same source. That's why 2018 was such an important case study. You had a major eruption, a summit collapse, and a 6.9 earthquake on the flank, all happening at once. The volcano went through its whole routine. The flank lurched half a meter, and then it stopped. It held together that time. Living on the south shore of the Big Island comes down to that phrase, that time. The slope holds and holds until eventually, on a timeline of tens of thousands of years, it gives way. Looking at the bigger picture, Kilauea isn't the only place where this happens. Every volcanic island that builds up out of the sea eventually faces this dynamic. They get too tall and top-heavy to support their own mass, and parts of them break off. The Canary Islands have their own well-known example with the Cumbre Vieja volcano on La Palma. Some scientists suggested it could drop a giant block into the Atlantic and send a massive wave toward the U.S. East Coast. Other researchers disputed that, arguing a collapse would happen in smaller stages rather than one clean break, producing much smaller waves. It's the same debate you see in Hawaii, one huge catastrophic drop versus a slow, step-by-step crumble. The reality probably falls somewhere in the middle, depending on the specific event. What nobody disputes is that these islands eventually break apart. The debris sitting on the ocean floor around Hawaii answers that question for good. The islands above water today, like Oahu, Maui, and the Big Island, are just the sections that haven't slid away yet. The parts that did slip are lying scattered across the seafloor miles offshore, showing what happens when a mountain finally gives out. Where does that leave anyone watching this unfold? It leaves us with a simple reality. The south flank of Kilauea is moving right now. The GPS data updates constantly, and the direction never changes. It points out toward deep water, 10 centimeters this year, 10 more next year, and a sudden shift of a few feet whenever a major quake hits. Somewhere further down the line, there could be a shift that doesn't stop. The researchers monitoring this aren't panicking, and there's no reason for anyone else to either. The chance of a massive collapse happening in our lifetime is very small. But small isn't zero, and geologists readily admit they can't point to the exact tipping point. For now, they watch the data feeds, check the buoys, and monitor the flank as it keeps doing what it's done for thousands of years, creeping forward